So in this video, hopefully I can briefly describe sound to you and its relation to distance, and maybe give you guys a better idea of what was going on earlier, meaning the physics behind the strings I was plucking. So what exactly is sound? I mean, we can't feel it, we can't grab it. What is it? Well, sound is basically created through a rapid variation in the density or pressure of air molecules above and below the current atmospheric pressure. So what I mean by that is something like a vibration occurs, me speaking right now or me playing guitar, and this vibrating body, this vibration, is going to cause the particles to compress and then decompress, and then compress and then decompress. They're going to fluctuate, and this fluctuation in pressure is known as a sound wave. Our brain understands sound through this sort of pattern of compressing and decompressing. Now, in physics, we can classify sound through something known as the sine wave. Here is the amplitude, meaning the compression, the max compression. Here is the decompression area. This is compression, decompression together, the max displacement. So we have a vibrating body of some sort, my voice or acoustic guitar. It's going to create a vibration, and air particles are going to keep smacking each other until they cause a max displacement up here, and then they're going to come down and displace and come back up. So the real filled in dotty part is right here, and the less filled in part's down here. And this is known as a cycle when these are combined. Now, the frequency of sound can actually be determined through counting these cycles out. I mean, you wouldn't be able to do that in real life. You can't really see these things, but hypothetically speaking, hertz, the term hertz means one cycle. So you can find hertz through this equation, which means frequency equals 1 over time, and time in this case is 2, because the graph says 2 seconds. And so what happens when we do 1 divided by 2, we get 0.5. So the frequency of this wave is 0.5 hertz per second. Interesting, right? Very, very little hertz. What exactly does that mean? Well, that means that it's going to have a lower, really, really low sort of, not low, that's not the correct word. It's going to have less cycles. It's going to be more spaced out. When it has a higher frequency, it's going to be really bunched up like this. The air pockets are going to be really bunched together. Alright, so there's also distance in relation to the pressure of sound. That's going to impact how we perceive sound, and it's going to change a lot of things. One of the formulas we can use, or one of the concepts I'm going to talk about, is the inverse square law. It states that as sound travels and is not impeded or not stopped as it travels, it's going to inversely fall. It's going to decrease in amplitude. The pressure is going to drop. Imagine if you drop a stone into a pond. There's going to be a bunch of waves cycling out. The waves that are closer to the rock that's dropped into the pond, those are going to be the powerful waves. You could also see it as front row of a concert versus the very back of the concert hall. Now, with the inverse square law, we can use a little bit of math to put this into play. Say this is me playing guitar. This is the first row. They're hearing it all cool. First row, one away. And then this is the second ring. This is 2 times the distance. D means distance. What's going to happen here is that the inverse square law says that you take the square of what the times is. So if I want to find out what the actual pressure is now, that it's 2 feet away, or 2 times the distance, I'll just basically do 1 over 2, and that equals 1/4. So what happens third row? Well, 1 over 3, 1 over 9th. So third row 1/9 the pressure of the source, which is me in the middle. Another way to look at this could be through a spray can. If you put a piece of paper up here, you're going to get darker colors. You're going to get the max amplitude, the max pressure out of the spray can. You're going to have more particles. But what happens as we space out? What happens as we go 2 times, 3 times, and 4 times out? Same idea, 1/4 the total pressure, 1/9, 1/16. This applies directly to sound. As a sound wave disperses, we're going to hear it softer. That's why if we move away, we hear a sound quieter. That's why if we move in, we hear it louder. Alright, so in regards to finding out how much a sound level drops, we're going to have to understand decibel. Decibel is just a measurement for the air displacement, the pressure displacement that occurs when a vibration triggers a sound wave. Formula we could use, 20 log 10. Looks kind of daunting in a way if you don't know about math, but all this means is, use 20 log 10, and let's say you're 2 times away. You plug it in the calculator, and what you're going to get is a value of 6. If you do the same thing again and say 4 times away, what are you going to get? You're going to get 12. So basically, this means you double the distance. It's going to be 6 decibels softer. If you quadruple, it's going to be 12 decibels softer. So if I'm 4 feet away, talking to you at 50 decibels, and I go to you 8 feet away, I'm going to be down to 44 decibels now. And you get the picture. The more you keep doubling, the more the decibels drop. This is known as the sound pressure level formula. You can use it in basically any scenario to determine the drop in decibels. In regards to sound pressure though, because intensity level is a lot different. But